Okay. Hi guys, my name is Asmari Patricia and I am here to present the power of machine learning. Machine learning is a captivating field of artificial intelligence and it empowers computers to learn from data without being spoon-fed or explicitly programmed. This revolutionary capability underpins many of the advanced technologies we use daily, from personalized recommendations to autonomous vehicles, or you could call them self-driving cars. And understanding its core principles is crucial for anyone navigating the modern data landscape. So we have two pillars in this. We have supervised machine learning and unsupervised machine learning. In supervised learning, models are trained on labeled data sets, meaning each input example is paired with the expected output. The goal is for the model to learn a mapping function from inputs to outputs, allowing it to predict outcomes for new unseen data. Then for unsupervised machine learning, it deals with unlabeled data sets. Here, the algorithm explores the inherent structure with the data, identifying patterns, clusters, or relationships without any prior knowledge of the desired outputs. It's about discovering hidden insights. So we have two models right here, which is the heart of prediction. We have the deterministic models and the probabilistic models. So what are they? These are the representation of the real-world phenomenon. They encapsulate the relationships and patterns observed in data, allowing us to make predictions or draw inferences. So for the deterministic model, these models hypothesize exact relationships between variables, assuming no randomness or prediction error. They are most suitable when the phenomenon being modeled is highly predictable and measurement errors are negligible, providing precise outputs for given inputs. When we go to the probabilistic models, these ones acknowledge and quantify uncertainty. They posit that observed data comprises two components, a deterministic relationship and a random error term. This approach is more realistic for complex systems where exact prediction is impossible. So the types of probabilistic models, we have regression models, correlation models, and other advanced models in their own category. So for the regression, we focus on predicting a continuous dependent variable based on one or more explanatory variables, quantifying the strength and form of their relationships. Then for the correlation models, we measure the statistical relationship between two or more variables, indicating how closely they move together without implying causation. For the advanced models, includes a wide array of specialized probabilistic models tailored for specific statistical challenges, such as time series analysis or survival analysis. So generally, these probabilistic models offer a robust framework for understanding and predicting outcomes where inherent variability exists. Yes. So for the regression model, a deep dive into it, there are steps. One is to hypothesize deterministic components. Formulate an initial theory about the direct non-random relationship between your dependent and explanatory variables. 2. Specify probability distribution of random error term. Define the statistical characteristics of the unpredictable variability, often assuming a normal distribution. Step 3, we evaluate the fitted model. Assess how well the model explains the observed data using various statistical metrics, checking for bias and precision. Lastly, step 4, use the model for prediction and estimation. Apply the validated model to forecast future outcomes or estimate values for unobserved scenarios, leveraging the established relationships. So we have the least squares method, a fundamental in finding the best fit line, which minimizes the sum of the square differences between the actual and the predicted y values. So we have the parametric versus the non-parametric models. So the choice between the parametric and non-parametric models depends on assumptions about the underlying data distribution and the flexibility required for the regression function. For the parametric models, you predefine the exact functional form of the relationship between variables, say the linear or the quadratic. And then this approach assumes a fixed number of parameters, which are estimated from the data. If the underlying assumptions hold, parametric models can be very efficient and offer strong statistical inference. So it assumes specific distribution, fewer data points needed, and They're easier to interpret. Then for the non-parametric models, models are flexible, allowing data to determine the shape of the regression function without making strong assumptions about its underlying distribution. They are particularly useful when the true relationship is complex and unknown, adapting to various data patterns. However, they generally require more data, so no distribution assumptions, more robust to outliers, and can model complex relationships. Yes, I was about to say one like yes, but it's okay. Then we have the classic IRIS dataset. It's the classification benchmark, literally. So the IRIS dataset is a quintessential benchmark in machine learning, particularly for classification tasks. It comprises measurements of various parts of 3 different species of iris flowers, providing a straightforward yet effective scenario for multi-class classification. The dataset includes 4 key attributes, all measured in centimeters. So we have the sepal length, that's the length of the sepal, the outer leaf-like part protecting the flower bud. Then we have the sepal width, the width of the sepal. We have the petal length, the length of the petal, the inner, often colorful part of the flower. Then we have the petal width, the width of the petal. So these attributes are used to classify each flower into one of the 3 iris species. We have setosa, versicolor, and virginica. So then we come to the k nearest neighbors, or you can call it the KNN algorithm. It's simple and yet a potent classifier. The k nearest neighbors algorithm is non-parametric. It's a lazy learning algorithm used for both classification and regression. Its simplicity and effectiveness makes it a popular choice, especially when little is known about the data distribution. So 3 steps are: compute the distance, find the k neighbors, and then find the majority vote. So the key considerations of KNN have the distance matrix. You can use the Euclidean distance for dimensions measuring similar properties, and then the Manhattan distance when dimensions are dissimilar. Normalization is crucial if features are equally important but on different scales. Then you have hyperparameter tuning. Crucially, never tune hyperparameters using test data. The objective is to evaluate performance on unseen data, and tuning on the test set compromises this goal, leading to an over-optimistic assessment of the model's generalization ability. So KNN is applied in different sectors and it has its own pros and cons. So the applications, you can find it in the text mining, agriculture, finance, and also in the Kaggle competitions. So the pros, it's easy to explain and understand, no assumptions or data distribution, fast choice with little prior knowledge, and works for regression and classification. It also handles multi-class datasets easily. The cons, we have efficiency declines in dataset size, expensive prediction steps such as the entire training set, suffers from skewed class distributions, and can't handle missing values. We have decision trees. That's where we find the purity, pruning, and the pitfalls. Decision trees are intuitive and powerful models, but their effective use requires understanding metrics from the genome impurity and strategic pruning to mitigate common issues. Purity metrics, we have the genome impurity, measures the frequency of mislabeling a randomly chosen element in the dataset. It ranges from 0 to 0.5 with lower values indicating higher purity. GENA is generally faster to compute than entropy as it avoids logarithms. Entropy is a measure of disorder or uncertainty in a data set ranging from 0 to 1. Higher entropy means more mixed classes, while more complex due to the low computations, it provides a similar insight into node purity. Then we have pruning strategies. We have pre-pruning and post-pruning. So for pre-pruning, halting tree construction early by setting parameters like maximum depth or minimum samples per split. However, this can be suboptimal as a seemingly weak split earlier on might lead to powerful splits later. Post-pruning, also known as cost complexity pruning, This involves growing a full tree and then systematically removing branches that do not contribute significantly to predictive accuracy. This is generally preferred for achieving better generalization. So the pros of decision trees we have: easy to interpret and visualize, no distribution assumptions, it's non-parametric, and it captures nonlinear patterns effectively, minimal data preprocessing required. It's useful for feature engineering, like predicting missing values, and then it handles binary, categorical, and continuous inputs and outputs. The cons: it's sensitive to noisy data, leading to overfitting. Small data variations can cause different trees, we'd call it high variance, and then biased towards imbalanced datasets. Greedy algorithms don't guarantee global optima, and data exponentially decreases with granting depth. Information gain can be biased towards attributes with many attributes. So we come to the ensemble learning, the power of collective intelligence. Ensemble learning is a powerful machine learning paradigm where multiple weak models are combined to form a single supermodel. The core idea is that a data collection of diverse, individually mediocre models can collectively achieve higher accuracy and robustness than any single strong model. Power of unity. So we have bagging, bootstrap aggregating. Bagging or bootstrap aggregating tackles a fundamental statistical challenge. That is, how to infer properties of an entire population from a limited sample. It ensures that our sample effectively represents the whole population. The central concept involves creating multiple models, each trained on a different bootstrap training set, and then averaging their predictions to produce a more robust and accurate final output. While bagging significantly enhances predictive accuracy, it often comes at the cost of interpretability, as the combined model's decision-making process can be more opaque. Random forest, a modified bagging approach. So the random forest algorithm is a sophisticated extension of bagging. It operates as a collection of decorrelated decision trees built with several key modifications to enhance performance and reduce overfitting. Bootstrapped subsampling. Each tree is trained on a random sample of the training data and drawn with replacement. Random feature selection. At each split point within a tree, a random subset of features is considered rather than all the available features. Then we have the decoupled tree growth. Trees are built independently using their respective random features and subsamples. So random forest has its advantages and considerations. So it's robust to outliers. The ensemble nature makes random forest less susceptible to anomalous data points. Then it can handle nonlinear data. It effectively captures complex nonlinear relationships within the data. And it lowers the risk of overfitting, because random feature selection and bagging help to prevent models from memorizing the training data. And it's efficient on larger datasets because the parallel nature of the tree construction allows for efficient processing and extensive datasets. However, random forests can be biased when dealing with categorical variables and may be slow to train. They're also less suitable for problems requiring high linear models and those with high density of sparse features. So we have boosting, we could call it sequential ensemble learning. Boosting deals with sequential trees and weighted samples. Bagging deals with parallel trees and random subsamples. Then shared, that's where the ensemble comes in, or the decision trees. So boosting offers an alternative approach to ensemble learning, fundamentally differing from bagging in its own function. While bagging builds models in parallel using independent subsamples, boosting constructs models sequentially. In boosting, each new model attempts to correct the errors of the preceding models. This sequential error correcting process often involves assigning higher weights to misclassified samples, focusing the learning on more challenging examples and leading to highly accurate models. So support vector machines, that's why we maximize the margin. Support vector machines, or you could call them SVMs, are powerful supervised learning models used for classification and regression tasks. By default, SVMs prioritize correct classification over maximizing the margin between classes. However, they're also adept to detecting and effectively ignoring outliers, which contributes to their robustness. A critical component of the SVMs is a kernel function. This function implicitly defines inner products in a transformed higher dimensional space, effectively allowing SVMs to find nonlinear decision boundaries without explicitly computing the transformation. This makes the complex pattern recognition feasible. The role of the kernel function in SVMs is basically to handle nonlinear relationships. It computes the similarity between data points and in a transformed feature space without explicitly performing the high dimensional mapping. This computational efficiency is a major advantage. For example, evaluating a common kernel function like the radio basis function RBF typically requires only one addition and one exponentiation compared to a simple dot product in the original space, showcasing its computational elegance. So we have gamma, the controlling influence in SVMs. So low gamma. A gamma value implies a large similarity radius, meaning points further apart are still considered similar. This results in a smoother, more generalized decision boundary, potentially leading to underfitting if too low. The gamma hyperparameter controls the distance of influence of a single training point. So selecting an appropriate gamma is essential for balancing the bias and the variance in the SVM model. So aside from the low gamma, we have the high gamma. So a high gamma is a value that indicates a small similarity radius requiring points to be very close to be grouped together. This creates a highly complex, often jagged decision boundary that tends to overfit the training data. So we have k-means clustering, and we have its strengths and weaknesses. So the simplicity and ease of implementation is brought by k-means clustering. Really? Are you sure? Of course not. So let's do this again. K-means clustering, its strengths and weaknesses. Simplicity and ease of implementation. K-means is a straightforward to understand and implement, making it a popular choice for initial clustering analysis. Then for the linear algorithm, it's considered a linear algorithm operating on a geometric means of clusters. It's really popular due to its simplicity and effectiveness. So k-means is one of the most widely used clustering algorithms. However, k-means has several limitations. It's only applicable when the mean is well defined and is highly sensitive to outliers and the initial selection of cluster centroids or seeds. Furthermore, it struggles with non-hyperellipsoid cluster shapes. Forgive my German. Okay, so lastly, but not least, we have the principal component analysis. Principal component analysis is a fundamental dimensionality reduction technique. Its primary objective is to transform high-dimensional data into a low-dimensional representation while preserving as much variance or information as possible. PCA operates under the assumption that variables exhibit linear correlations. If correlations are nonlinear, PCA may not be effective. PCA performs lossy compressions, meaning some information is discarded when insignificant components are removed. Proper scaling of variables is crucial, as different scaling methods can yield varying results. It's important to document the scaling used and avoid adjusting it based on prior data knowledge. Interpreting principal components can be challenging, as they are linear combinations of original features, making direct translation to original contexts difficult. PCA is widely applied in image compression, preprocessing of various machine learning tasks like classification, regression, clustering. It's also used in face recognition by igen faces and data visualization. Thank you so much for giving me your time. And that's my presentation. Once again, my name is Asimere Patricia.